this is how many steps of the phase you have. Usually it's 1 or 2, right? So, so for example, here's a table from Summerjai's book that he used to indicate the step services. So here you have, for example, 544, this top one, can be broken down into 4, can be broken down, okay, so this is notation 9111 by 100, for example, okay? So if you are talking about 711, then it will be step 4100 by 111, okay? So that's how Summerjai's notation related to high mirror services. The point is, high mirror services, what he found is the one key point he found is that if you have a high mirror index services, not no mirror index services as is 100 or 111, this sort of thing, like these with a lot of big number in the indexes, then then that service is very reactive. So the more high mirror index services are more reactive than low mirror index services. Okay, so this is the equivalent. I gave an example down here. 10870 is equal to 711, 3100. Of course, it depends on what is the service structure. Is it FCC or ECC kind of thing. So here's how it looked like. So he has a very nice diagram in his book. So you can take a look at Summerjai's book on this. So these are the step services that you see at different high mirror index that you write down for FCC service. All metal. He liked to study metal services, and because metal services you can prepare quite nicely by polishing in a nice way. Are you okay on the both side? Okay, thank you. So it could be, you could step in one way or you could step in 2 ways, because here you can see that you can sort of going in a slanted direction in some of these step services. Okay, so I have so those are what I like to talk about the crystallography. Now, what I want to do is to talk a little bit about how we measure this, how we know actually the crystal structure of the surface that we're looking at. Okay, so I talk a little bit about diffraction. Once again, diffraction is a key thing that we use. So in particular, instead of X-ray diffractions, you can look at electron diffraction. X-ray, you can't really use X-ray diffraction to look at surfaces because the X-ray penetration depth is a lot, because you examine the entire both the cell edge and the substrate region at the same time. So it really is not that useful. What you want to use is that some particle that have a very short mean free path, and so the electron is qualified to be this. If you choose the right energy, you can choose the interaction region, and you can make it in such a way that it only interact with the surfaces of short mean free path. Okay, so electron diffraction as a mean to look at surface structure, and in this particular case, we look at electron diffraction, in particular low energy electron diffraction under 200 electron volt. So you remember around 150 volt electron volt, the Debye wavelength for the electron, right, is about 1 angstrom. So that is the right energy for diffraction to occur, because your wavelength should be similar to the periodicity of the thing that you are diffracting from. Okay, so I would like to talk to you about low energy electron diffraction, commonly known as LEED, right? That's the jargon that people use, and in fact, you know, in addition to Debye, people discovered electron diffraction way back in the early days of quantum mechanics, and this is one way to prove that indeed diffraction the key, right? Is the key, diffraction phenomenon is the key to prove that all matter is made out of both particle and wave. You remember the famous Thomson father and son Nobel Prize, right? The father, Thomson, is J.J. Thomson is the guy who invented or identified electrons, right, as a particle. The son, George Thomson, little known George Thomson, also got the Nobel Prize 20 years later, I think, for discovering diffraction phenomena. So electron diffraction was sort of a father and son effort. So George Thomson was the guy who diffract from nickel wire. He saw nickel wire, electron diffraction from nickel wire, and that essentially verified the idea of de Broglie that things that can occur both as particle and wave. So here, the electron is often think of particle, but it can exist as a wave. It can generate wave phenomena. So that's an important history about electron diffraction. So in a modern day electron optics, that what people do is that you have a bit of an electron gun. It's basically a tungsten wire. You heat it up thermally and emit electron. And the electron, you have some sort of optic to focus your electron beam down to your sample. Okay, and so and diffraction phenomena occur. I draw this wiggle line, the red line as a wave coming out, and usually you have several grid, spherical grid, and then you have a phosphor screen. There's a high voltage between the last grid and the phosphor screen. So when the wave make it down to the last grid, it got sucked right in, accelerated, and hit the phosphor screen, and you see spot. Okay, so that's essentially it. So that's what you see. So you look down from your window, right? This is, so you look this way, your eye look this way, sorry, your eye look this way, and then you see the back side of the electron gun, and then you see the diffraction pattern on the phosphor screen, like this. And this looks something like that. Okay? There's actually a very good Canadian company based in London, not very far from here, about 100 kilometers from here. In fact, by the name of Osipa, and he used to work for, Professor Rutkowski at the Guelph side, and he started his company called OCI Microengineering, actually building reverse wheel lead. This is a so-called lead optics, and it actually become one of the strongest players nowadays in terms of lead manufacturer. So he's a very, he has expanded his company based in London, and in fact, there's a connection to Guo Guolu because he worked at Guo, used to work before he started his company. And he's very successful in building lead optics like this. Okay? And we have bought, in fact, one of his lead optics like that. Okay, so that's what happens. So you have the electron diffraction, you have lead optics, and usually you label this spot. You always call the primary beam, which you don't see really, because you always, the direct beam comes back is still 0, and then the one on the side. So this one, for example, is called 1, 0 beam, 1, 0 reflect, and this is negative 1, 0. These are just labeling systems that you label when you talk to electron diffraction people, then you identify which beam that you're talking about. There are two things you can get out from this diffraction pattern. First of all, you can see the pattern, the relative pattern, and what is characterized by this pattern. You have the strong beam, right, all the bright spot, and then you have the faintest spot. The bright spot are usually the substrate spot because those are coming from the substrate. The less intense spot are coming from the overlayer. So that's one thing, the pattern itself.